fossil evidence of hibernation-like state in 250 million year old Arctic animal. Hibernation is a familiar feature on Earth today. Many animals, especially those that live close to or within polar regions, hibernate to get through the tough winter when food is scarce. Temperatures drop and days are dark. According to a new research, this type of adoption has a long history. In a paper published on August 27th in the Journal of Communications Biology, scientists at the University of Washington and its Baruch Museum of Nature History and Culture report evidence of a hibernation-like state in an animal that lived in the Arctic or Antarctica during the early Jurassic, some 250 million years ago. The creature, a member of the genus Lysirotrosaurus, was a distant relative of mammals. Antarctica during Lystrosaurus time lay large within the Antarctic Circle like today, and experienced extended periods without sunlight each winter. The fossil are the oldest evidence of the hibernation-like state in a vertebrate animal, and indicates that torpor, a general term for hibernation and similar states in which animals temporarily lower their metabolic rate to get through a tough season, arose in vertebrates even before mammals and dinosaurs evolved. Animals that lived at or near the poles have always had to cope with more extreme environments present there, said lead author Megan Whitney, a postdoctoral researcher at Harvard University who conducted this study as a UW doctoral student in biology. These preliminary findings indicate that entering into a hibernation-like state is not like a relatively new type of adoption, it is an ancient one. Lysitrosaurus lived during a dynamic period of our planet's history, arising just before Earth's largest mass extinction at the end of the Primid period, which wiped out about 70% of vertebrate species on land, and somehow surviving it. The stout four-legged foragers lived another 5 million years into the subsequent Jurassic period and spread across swathes of Earth's then single continent, Pangaea, which include what is now Antarctica. The fact that the Lystrosaurus survived an end-Permian mass extinction and had such a wide range in the early Jurassic has made them a very well-studied group of animals in understanding survival and adoption, said co-author Christina Sidor of UW, professor of biology and curator of vertebrate paleontology at Burke Museum. Paleontologists today find Lystrosaurus fossils in India, China region, part of Africa, and Antarctica. These squat, stubby creatures, most were roughly pig-sized, but some grew 6 to 8 feet long and had no teeth, but bore a pair of tusks in their upper jaw, which they likely employed to forage among ground vegetation and dig for roots and tubers, according to Whitney. Those tusks made Whitney and Sidor's study possible. Like elephants, Lystrosaurus's tusks grew continuously throughout their lives. The cross-sections of fossilized tusks can harbor life history information about metabolism, growth, and stress or strain. Whitney and Sidor compared cross-sections of tusks from 6 Antarctic Lystrosauruses to cross-sections of 4 Lystrosauruses in South Africa. Back in the Jurassic, the collection sites in Antarctica were about 72 degrees south latitude, while within the Antarctic Circle at 66.3 degrees south. The collection site in South Africa were more than 550 miles north during the Jurassic at 58 to 61 degrees south latitude, far outside of the Antarctic Circle. The tusks from the two regions showed similar growth patterns with layers of dentin deposits and concentric circles like tree rings, but the Arctic fossils harbored an additional feature that were rare or absent in the tusks farther north: closely spaced thick rings, which were likely to indicate periods of less disposition due to prolonged stress. According to the researchers, the closest analog we can find to the stress marks that we observed in Antarctica, Lystrosaurus's tusks, are the stress marks and teeth associated with hibernation in certain modern animals, says Whitney. The researchers cannot definitively conclude that Lystrosaurus underwent true hibernation, which is a specific weeks-long reduction in the metabolism by temperature and activity. The stress could have been caused by another hibernation-like form of torpor, such as a more short-term reduction in metabolism, according to Sidor. Lystrosaurus in Antarctica likely needed some form of hibernation-like adaptation to cope with life near the South Pole, said Whitney, though Earth was much warmer during the Jurassic than today, and parts of Antarctica could have been forested by plants, and animals below the Antarctic Circle would still experience extreme annual variations in the amount of daylight, with the sun absent for long periods in winter. Many of other ancient vertebrates at high latitudes may also have used torpor, including hibernation, to cope with the strains of winter, Whitney said, but many famous extinct animals, including the dinosaurs that evolved and spread after the Lystrosaurus died out, don't have teeth that grow continuously. To see the specific signs of stress and strain brought on by hibernation, you need to look at something that can fossilize and grow continuously during the animal's life, said Sidor. Many animals don't have that, but luckily Lystrosaurus did. If analysts of additional Antarctic and South African Lystrosaurus fossils confirms this discovery, it may also settle another debate about ancient hardy animals. Cold-blooded animals often shut down their metabolism entirely during a tough season, but many endothermic and warm-blooded animals that hibernate frequently reactivate the metabolism during the hibernation period, said Whitney. What we observed in the Antarctic Lystrosaurus tusk fits a pattern of small metabolic reactivation events during a period of stress, which is the most similar to what we see in warm-blooded hibernations today. If so, this distant cousin of mammals isn't just an example of a hardy creature. It is also a reminder that many features of life today may have been around for hundreds of millions of years before humans observed them.